Hey there, in this video we're going to look at the issue of rounding error that can crop up when we work with floating point numbers. And we're going to inevitably be working with a lot of floating point numbers in this class. And so this is something we need to be well aware of. At the heart, the issue is that a computer cannot store an infinite number of decimal places. It would require an infinite amount of memory in our computer to be able to do that. So instead, our computer stores a lot of decimal places, something like 55 decimal places, but not infinity decimal places. For a lot of simple calculations, 55 decimal places is plenty, but there are cases where we're going to run into trouble. Let's start with a real simple example. If I want to take 0.1 and add it to 0.2, the result is 0.3, of course, right? But let's look at what the computer just did. It said 0.3 mostly, but then out here there's an extra little 4. So what's going on there? Or what if I do 0.1 plus 0.2 minus 0.3? Now, mathematically, the answer should be 0, right? But if I run that in my computer, I don't get exactly 0. I get a very tiny number, but the number isn't 0. So what if I had code that was checking if 0.1 plus 0.2 equaled 0.3? Would that code ever run? And the answer is no. If I was specifically checking for equals to 0.3, that code would never ever trigger because we wouldn't be exactly equal to 0.3. So what is going on here? I mean, it looks like things are just really broken already. So let's look a little bit more closely. Let's print some of these values with a little bit more precision. So what I'm going to do here is I'm going to use some more advanced formatting for what we're printing. So if I want to format the thing I'm printing, I use a little F before my quotes. It means I want to make a formatted string. This is a feature they added in Python. I don't know if it was 3.5, 3.6. I mean, a few versions back from where we are now, but it's a relatively new language feature. And the way formatted strings work is if you put them in brackets here, the same kind of brackets you'd use for dictionaries, although just as a coincidence. If you put a value in there, you can format it. So if I want to format 0.1 as a 55 decimal place floating point number, I would do 0.1 and then my formatting after the colon, 0.55f for float. Don't worry, all this stuff is spelled out somewhere. There's a web page, and we'll talk a little bit more about formatting in a later video. But for now, understand that what this does is it tells Python I want to print, not all, but I want to print 55 decimal places. Otherwise, by default, Python is not going to show you all of what it's kept track of. And if I print 0.1 to 55 decimal places, I can see that it's not actually equal to 0.1. It's 0.1 mostly, and then there's some extra stuff here. What's going on? Well, what is going on is that 0.1 is a repeating decimal if we represent it in base 2, if we represent it in binary. And the way a computer works is it represents all of your values as binary numbers. Like, so for example, if I want to represent the value 3 in my computer, the way the computer represents that is in binary is as a bunch of zeros and then 1, 1. I'm only allowed to use zeros and ones. And what this represents here is we've got the, at the very end here, we have the ones place, and then next to that we have the twos place. And so this would be the value 3. Kind of like in decimal. Or if I wanted to represent the value 33 in decimal, then that would look like, well, it look like a bunch of zeros and then 3, 3. Where in decimal we have the tens place. A little hard for me to fit that in here. The tens place, and then we have the ones place. Space this out a bit. Okay, so 33 is 3 tens plus 3 ones. Well, on a computer, we're going to do everything in binary. So the number 3 is 1, 2, and 1, 1. Now, if we want to do decimal places in decimal numbers, you know, we would say, following that, we would have 1/10, or 4/10 in this case. We would have 500ths, we would have 6,000ths, and we'd have those all added together. And if we want to represent certain values in decimal, sometimes we run into trouble. Like if I want to represent 1/3 in decimal, that's equal to 0.3 repeating. I need an infinite number of decimal digits to get there. I can't get exactly 1/3 by adding 1/10 plus 1/100th plus 1/1000th. Any combination of hundredths, tenths, 1,000ths, 10,000ths will never ever be quite equal to 1/3. We always need more and more of them to get closer and closer. So just like you can have repeating decimals in base 10, you have repeating decimals in base 2 in binary as well. And as it so happens, 0.1 is a repeating decimal, 0.2 is a repeating decimal, and so is 0.3. They're all repeating decimals in base 2, and so we would need an infinite number of digits here to get this to be exactly equal to 0.1. So the way our number here, 0.1, is represented is, if we think about 0.1, we would need a half is too big, a quarter is too big, an eighth is too big, but a 16th. So 1/16 is going to be in there. I don't know, what other powers of 2 you would have in there, but you would need an infinite sequence of these powers of 2 to be able to represent the number 0.1. Okay, so we don't quite get there with 0.1, or we're not exactly equal to it in 0.1. If we try 0.2, it's a similar kind of problem. And likewise, if we look at 0.3, we also have this issue. So we go out pretty far. We're out here at, I don't know what that'd be, 12 or so decimal places, but beyond that, we start becoming inaccurate. And so this could hurt us a lot, especially if we are working with really close values to one another. If we have subtraction of really close values, your computer will be completely unable to distinguish the difference between 0 when you subtract them and, say, 10 to the minus 17. So the solution here is to be aware of this issue. You would never want to test if 0.1 plus 0.2 equaled 0.3. You would have to test if it was close. So the way you would write that is, instead of 0.1 plus 0.2 equaling 0.3, you'd write the subtraction and then check that the subtraction was less than some small value, like, I don't know, 10 to the negative 10 or something. That's how you would test that it was close enough to equal. All right, so be careful. You usually don't want to test for 0 exactly, but just close to 0 or really small. Another issue we can run into here is running out of decimal places. So for example, let's say I had the number 10 to the 100. If I want to write really large or really small decimal places, I use an E here to stand for times 10 to the, so E for exponent, kind of like the E button on a calculator. So if I wanted a really large floating point number, I'd write, like, say, E to the 100. If I took E to the 100 and I subtract 17 from it, that should be 17 less than E to the 100, but of course my computer is going to say, yeah, that's E to the 100. I don't have enough decimal places available to distinguish this value. Okay, so we've lost the difference there. It's just not able to show up with the precision we have in our computer. If you've ever worked with sig figs, and surely you have worked with significant figures, it's the same kind of issue in our computer, but our computer is always going to be cutting off after something like 55 significant figures, always cutting off there. And so you get whatever rounding issues you get when you truncate your decimal numbers. All right, I think that's a good place to stop for this video. In the next video, we're going to look at how we can do comparison. So I mentioned the danger of comparing 0.1 plus 0.2 to 0.3. We're going to look now how we do those comparisons in general.